session of the last day of the series of lectures. Now, today in this session we will continue the discussion on fluid machines. In the last class we had a discussion about the basic principles in general for a fluid machine, and today we will discuss in two lectures about two important hydraulic machines. First up we will discuss one reaction turbine, and the second class we will discuss hydraulic pump, centrifugal pump, mainly the centrifugal pump. So, today we will start the discussion in this class about a reaction turbine. Now, if we recall our discussion about the turbine, we know for a turbine if you remember, the head delivered or developed by the turbine H is given by these nomenclatures you already know, VW1 U1 minus VW2 U2 is by G per unit weight, where VW1, VW2 are the wheeling components or tangential components of velocity, absolute velocity of water at inlet to the turbine runner and outlet from the turbine runner, and U1, U2 are the inlet and outlet velocity of the rotor. And this can be written also, we have seen, in terms of the different velocity components like that. This has been done earlier by 2G plus U1 square minus U2 square by 2G plus VR2 square minus VR1 square by 2G. Here V1, V2 are the absolute velocity of the fluid at the inlet and outlet of the runner, U1, U2 are the rotor velocities, tangential velocity of the rotor, and VR is the relative velocity at the outlet to inlet 1. We have also recognized that this head delivered by the turbine is contributed by three parts. One part is dynamic change in the dynamic head, that means change in the kinetic energy. This is by the impulse action, and this is the head delivered. So, this is greater than this. So, this to be positive, V1 has to be greater than V2, and it happens for turbine that the velocity at the outlet is less than that at the inlet. So, therefore, this is a positive, means this contributes to the head delivered. Similarly, this to be positive, U1 has to be greater than U2, which means that in a radial flow turbine, the inlet velocity should have a higher rotor velocity, inlet point rather, and outlet point should have a lower rotor velocity. That means, in a radial flow the inlet will be at a higher radius, outlet will be at a lower radius. This has to be radially inward flow. That is why turbines are radially inward flow, and this has to be positive. VR2 has to be greater than VR1. That means, when it flows through the runner blades, the relative velocity, that means the velocity relative to the runner blades, has to increase at the outlet from the inlet. That means, this should provide a converging passage of the flow through the runner. So, with this concept we proceed. This contributes to static head, that means change in the static pressure, that means static pressure is decreased, static pressure decreased, and this is kinetic energy of the fluid decreased. So, combination of the decrease in kinetic energy and static pressure, we get the head delivered. Based on this, this is on the background. Now, we will discuss the turbine. Now, next which we will discuss is this. Based on this, we will discuss first a radial flow. We will discuss a radial flow reaction turbine. The first radial flow reaction turbine was defined. This is known as radial flow because the flow is mainly in the radial tangential direction. It is not purely radial, it has got both radial and tangential component, as I will discuss now, but it is known as radial flow reaction turbine, where these terms are non-zero in the runner. As we have discussed, there is a degree of reaction. So, this is 0 for non-reaction turbine or impulse turbine. So, this is a radial flow reaction turbine which was first invented by the scientist James B. Francis, and according to whom the radial flow reaction turbine, which was first found or invented is known as Francis turbine, and this is one of the very popular turbines which is used in hydraulic power stations. Now, I will describe what a Francis turbine, a radial flow reaction turbine is. Yes. Now, this you see, this is a radial flow reaction turbine. This is Francis turbine, is a typical radial flow reaction turbine, Francis turbine. Now, you see the water approaches this turbine, this is the turbine. Before coming to that, I tell you the water approaches the turbine from a reservoir at high altitude via a long pipeline, That means the water comes, water is the working fluid for this turbine, hydraulic water from reservoir at high altitude, from reservoir at high altitude. At high altitude water comes via long pipeline, and this pipeline is known as, in the terminology of the hydraulic power plant or hydraulic machines, this is known as penstock. Penstock is the long pipeline that leads water from the reservoir at high altitude to the turbine. Now, you see this is the turbine, is the starting point. So, water first comes, the first part of the turbine, which is a typical spiral casing, the water flows in this direction, and when the water flows through the spiral casing, this is known as volute casing, as it is written here, volute casing, or sometimes this is known as scroll casing. Now, when water flows through this casing, it enters here. Now, what happens when it flows through this casing, scroll casing, is a convergent type, its area is reduced. Now, here you see another component part of the machine is this number of static vanes, which are known as guide vanes. It is written here guide vanes or wicket gates, and they are all pivoted at this point, so that they can be swivel if required by about this pivot. So, there are number of pivoted stationary guide vanes frame fixed in a ring. So, therefore, there is a ring of stationary guide vanes or wicket gates. Now, what happens when the flow comes here in this scroll casing, the fluid enters into the passage of these wicket gates, passage formed by the wicket gates or the stationary guide vanes. So, the purpose of decreasing this area is to make the flow velocity in this direction constant. Why? Because when the flow is coming, how? Not why, how? The flow is coming, the flow is also entering into the passage. So, therefore, the volume flow rate, if you consider, flowing through this passage is getting reduced. Well, because the flow is entering here. So, if we have to maintain the velocity constant throughout this passage of flow, so we have to reduce the area in proportion, so that velocity remains constant. And to maintain the constancy of velocity is because of a smooth entry to this passage. Now, this passage formed by this guide vanes, stationary guide vanes, are converging passage. That means it is similar to a nozzle. So, converging passage, what does it do? It increases the velocity and decreases the pressure. Now, try to understand when the liquid or water, for example, here water from a high altitude reservoir comes through this line, at the inlet at this point or at this point anywhere in this scroll casing, the pressure is high, velocity is low. There may be a little loss because of due to the penstock skin friction. So, therefore, if we consider the loss, it is the loss that is the head available in the reservoir at altitude minus the loss. So, therefore, fluid comes here with a high energy, mostly in the form of pressure, but a low velocity. So, therefore, when the fluid enters this passage, converging passage, which acts as a nozzle, the velocity is increased because of the converging passage and the pressure is decreased. So, therefore, it converts a part of the pressure energy to kinetic energy at the outlet of these static vanes, and these static vanes, guide vanes or wicket gates, form the stator of the, this can be told in general, the stator of the machine, fixed part. Now, this is the moving part, you see the moving part contains, this is the shaft, and this is the rotating disc. This is the rotating disc, and number of radial vanes of curved shape like this is mounted on the disc, and the disc with the vanes mounted on it rotates. This rotates, there is a rotation, it is seen, this rotates. So, therefore, this is the rotating part of the turbine, which in the terminology is known as runner. Runner. That means this part, this is the rotor part of the machine. Rotor of the machine, which is the moving part which rotates, is known as runner, which consists of a disc mounted on the shaft, and on the disc there are radial vanes mounted on it. Now, these blades are known as runner blades. Now, when the fluid enters the runner blade, it has both pressure and velocity, because the velocity is generated, some high velocity is generated because of this conversion of pressure energy to kinetic energy while the fluid flows through the guide vanes, stationary blade passages. Then it flows through the runner in the radial inward direction, and it exchanges energy by the impulse action, it kinetic energy, and its absolute velocity is reduced, the relative velocity increases and pressure is reduced. This is the situation, as I have known that the relative velocity has to increase to decrease the pressure and to get the head delivered. Then finally, this comes here at the outlet, and then it is discharged, that means it is turned in the axial direction, that means in this direction, and then it is discharged. Usually this Francis turbine in most of the installation is in the horizontal plane, and the shaft is in the vertical plane, that the shaft is vertical. So, therefore, the fluid at the outlet from a radial direction is just turned 90 degree to the axial direction, and then it is discharged. And before discharge, it passes through a divergent tube known as draft tube, which I will explain now. So, this is the overall view or a schematic view of a reaction turbine called Francis turbine, hydraulic reaction turbine, and the flow diagram. Now, before proceeding to the next, we will first understand that in general for a reaction turbine, what is the net head across a reaction turbine. Now, we will see that what is the net head across a reaction turbine. Okay. Let us have a concept about the net head across a reaction turbine, the head available at the turbine, inlet to the turbine. These are very important things we have to know. Now, let us have an understanding like that. Let I write head available and net head. Let us have an understanding of that. Let us consider here a reservoir at an high altitude. Now, this is the penstock, this is the penstock. Now, this leads to the fluid and this water, and this is the turbine, and this is in the horizontal plane, the turbine as I have discussed. Then the liquid or the water turns this way, and this is the draft tube. This tube is the draft tube which finally discharges in this level water, which is known as tail race by the terminology, or tail water level, where the liquid is discharged or the water is discharged. Okay. Now, let us understand all these things. Now, from this datum at the tail race or tail water level, this height of the reservoir is denoted by H0. Now, this I will come afterwards. Now, you see, therefore, the gross head available is H0. Gross head means energy per unit weight is H0, because this is the potential energy of the water which is being utilized to develop power. So, the gross head is H0. Now, at the inlet, this point 1 to the turbine, what is the head H1? That is the head available for the turbine, that is head at inlet to the turbine. This head at inlet to the turbine is head available is the sum of the pressure head P1 by rho g, then sum of the velocity heads plus the potential head, because we are defining the datum here, the reference datum, and it is represented as Z. So, this is the head available here. Now, if we write Bernoulli's equation between a point here and the point 1, we can write here that pressure is 0 because we are considering all pressure above atmospheric, it is the atmospheric pressure, no velocity, only the potential head which is H0. This must be equal to the pressure here P1 by rho g, which is above the atmosphere because we have considered 0, plus V1 square by 2g plus z plus the losses which takes place in the penstock. So, therefore, you see that this is the head available at inlet to the turbine. So, head available at inlet to the turbine is H0, which now comes from a common sense. Even by a child, they can tell, oh, this is the gross head. So, head available at the turbine or inlet to the turbine will be this gross head minus the losses that it incurs. These losses is the skin friction losses. If there are some expansion, contraction, that losses, bend losses, all these losses together gives this H1. So, this is given here is H1, which is the head here, and this head corresponds pressure here, velocity and the potential head. So, this is written that in scale this is the pressure head, velocity is less, penstock is of large diameter. So, velocity head is less, it is shown like this, pressure head is large and this is. So, jet plus pressure head plus the velocity head, total head is shown here as the H1. So, therefore, H1 is the head available or inlet to the turbine. Now, next thing is that very important, net head producing work. So, the head which produces work from the turbine is this inlet head minus the outlet head. Now, since we have a draft tube that the turbine does not discharge directly in the atmosphere, turbine is set at a level jet from the tail water level, at a higher level from the tail, the base water level. So, therefore, since we add this tube, this is a part of the turbine. So, therefore, 3 is the point of discharge. So, therefore, we can write that we can now write this, if you like to see, I think this will be the best way of visualizing this. Now, you can see that the head producing the work H is the net head producing the work. So, you can see that H is the net head producing the work. So, net head producing the work is head here minus head here. So, net head producing the work is H1 minus H3. Now, you see what is H1? It is P1 by rho g plus V1 square by 2g plus Z1 minus, now here if we consider velocity is V3 minus V3 square by 2g, because here the potential head is 0 and the pressure is atmospheric. Now, we see what is the implication of this. When we add a draft tube, the velocity is reduced because it is divergent in nature. Now, if we do not have a draft tube, the turbine discharges into atmosphere, the velocity is high. That means, if we consider a point here at the outlet of the turbine runner, then V2 is higher than V3. That means, we will have a higher loss of kinetic energy. This kinetic energy is lost, which is discharged into the tail race, it is lost. So, therefore, to reduce the kinetic energy loss, we add a divergent tube so that the velocity is reduced almost to a negligible value, and then we get a higher head, effective head across the turbine. This is like this. That means, this net head is equal to the head available at the turbine. Already I told you H1 minus V3 square by 2g. Of course, if you write the friction taken into account into penstock, H0 minus H8 minus V3 square by 2g. This is H1. Now, I just show you, if instead of a draft tube I could have discharged this at 2, then what could have been the net head? In that case, net head without draft tube, without draft tube, without draft tube. What is the net head? Net head could have been H1 minus, now the velocity is V2 square by 2g, pressure is atmosphere because we are discharging into atmosphere, minus the jet. Why? Because this is the total head here, because the turbine is set up at a higher altitude or higher height from the tailwater level. So, therefore, this is much higher, V2 is greater than V3. Moreover, this height above which from the tail race the turbine is installed is coming into picture. So, therefore, net head is decreased. So, the purpose of this tube, draft tube, is to reduce the loss of kinetic energy at the exhaust, and at the same time we can set the turbine at a higher height from the tail water level because of practical simplicity or practical advantage without losing any effective head from the turbine or enhancing the effective head from the turbine. This is the purpose of the draft tube, which should be made very clear. But now one danger is there. When you make a draft tube, danger is that now if you write the Bernoulli's equation at 2 and 3 for the draft tube, then you write P2 by rho g plus V2 square by 2g plus z is here the atmospheric PA. Now, I write this in terms of the absolute pressure, then you can understand PA by rho g plus V3 square by 2g, and if you take care of the frictional losses plus HF. So, therefore, you see that P2 by rho g is becomes PA by rho g plus HF minus, what is this, minus V2 square minus V3 square by 2g. So, writing the Bernoulli's equation at inlet to the draft tube, that means at outlet to the runner and at the tail race level, we get an equation which tells the pressure at the inlet to the draft tube or outlet from the runner is less than the atmospheric pressure. HF is usually very small, we can neglect it. Minus Z, yes, yes, minus Z, yes, minus Z, this Z taken this side. So, by an amount this Z is positive quantity, minus Z, V2 minus V3 square, V2 square, V2 is higher than V3, it is reduced. So, therefore, by this amount this is getting reduced. So, therefore, again if I write, the space was less because I wanted to write, you can see with the figure. So, therefore, the pressure, if you neglect the friction, so pressure at the inlet to the draft tube or at the outlet from the runner is reduced by this amount V2 square minus V3 square by 2g plus j. That means there is a danger that if you set the runner at a very high height and you are very happy that it does not matter in the effective head across the turbine, and if you reduce V3 like anything from V2 very less, V3 is very less, then you have to check that this P2 is also going to be lesser than the atmospheric pressure, that means there is a suction created, that P2 there is a suction created, which is actually this is the problem of good teaching. The suction created is technology or teaching, you have to choose any two, any one, okay. So, then therefore, this we have to be very cautious that this value should not be very high, so that the P2 becomes lower, much lower than the atmosphere. Why? When P2 should always be greater than the vapor pressure of water at that temperature. If P2 falls below that or close to that, then water will start boiling, and this phenomena is known as cavitation. If the vapor pressure is reached at that temperature at which the water boils, then the water starts boiling. Even at a lower temperature than the vapor pressure, the air first, dissolved air first starts releasing at a high velocity, and that creates some problem which I will tell if I get time afterward. This is the cavitation, this is one danger. Now, after this I will discuss the runner of a Francis turbine. Now, how does the runner looks like? Now, I tell you before that the Francis turbine is a reaction type of turbine, reaction. Now, here it has been found this type of turbine that this technology and teaching does not go parallel. So, reaction turbine is a turbine already I have told by definition that it works on the principle that pressure release is taking place in the runner. Now, in a reaction turbine, one main thing is that this shape of the runner depends upon the specific speed of the turbine, which I already discussed earlier, that is n p to the power half h to the power 5 by 4. This is the h to the power 5 by 4. I think they cannot see this h to the power, now they see fine. Now, the specific speed of the reaction turbine actually works well or efficiently when the head is low. Specific speed is rather relatively high as compared to an impulse turbine. So, when head is low, we want to run a machine at its efficient condition. Then to get a finite power or a substantial power, you have to make the flow increase, that means flow should be high. So, therefore, turbine runner blade should be designed in such a way that it accommodates more flow. So, flow rate should be high through it, and at the same time with the high flow rate at the runner outlet, velocity has to be low because it has to avoid the cavitation. We have seen for cavitation that the velocity at the runner outlet should be low, it should not be high. That means it should accommodate a high flow rate, so that even at a lower head it can develop a substantial power efficiently, but at the same time the velocity at the runner exit has to be low. So, these are the considerations which are to be made to design a runner blade. Now, let us see a typical runner blade. A typical runner blade looks like this. A typical Francis runner blade looks like this. Now, this runner blade, this is the inlet one, this is the outlet, this is the direction of the tangent, that means the tangential velocity u. So, this is the inlet. Now, if I draw the velocity triangle at the inlet, so it will look like this. It will look like this. This is the inlet tangential velocity. This is the radial velocity. I told always we will assume a shockless entry, that means this is tangent at here. The direction is same as the blade angle, and this is the absolute velocity V1. And this angle is alpha 1, and let us define this angle as beta 1. And this is the, as I have told, the component, this is the flow velocity Vf1. Well, so this is Vr1, this is Vr1. So, this is this perpendicular, this is, so I draw it again that the, so that you can understand better. So, this is like this. So, this is beta 1, this is Vr1, so that you can see this clearly. This is Vf1, this is Vf1. Well, so you have to understand this very clearly. This is V1 and this is Vr1. And you see here U1 Vr1 is equal to V1 minus U1. So that you can write V1 as Vr1 plus U1. So, you draw the triangle like that, U1 plus Vr1, this becomes equal to V1. Now, at the outlet, if I draw the triangle, the outlet triangle is like that. Now, in a Francis runner, what is done? The outlet velocity is made radial. That means there is no tangential component at the outlet. The runner is designed in such a way that the tangential component in the outlet becomes 0. So, therefore, this V2 is nothing but Vf2, the flow velocity out the outlet, because flow velocity is by definition is the radial component of velocity. So, therefore, this is Vr2 and this is U2. So, here also the similar way Vr2 is V2 minus U2. If you write this vector equation, then this vector triangle you can understand. So, therefore, this is beta 2, and here this angle is by definition alpha 2. Alpha is the nomenclature given to the angle made by the relative absolute velocity in the tangential direction, which in this case 90 degrees. Moreover, the blades are designed in such a way that the flow velocity through the blade passage is constant. That means Vf1 is Vf2 is constant. Let this is Vf. Now, I find out the value of the head that is being developed by the runner. So, head I know that developed by the runner, head developed is head developed which is nothing but H1 in our earlier H developed, rather I write H developed. H developed equals to VW1 U1 minus VW2 U2 by G. Now, in this case this is 0 because VW2 is 0, it is a radial outlet. That means V2 is radial, V2 is Vf2. So, this becomes is equal to VW1 U1 by G. Now, a little bit geometry and trigonometry school level, that VW1 is this one, this is VW1, this is VW1, this is VW1, which in terms of Vf1 this is here VW1, this is VW1, VW1. This is in terms of Vf1 is Vf1, if I represent in terms of alpha 1, this is Vf1 cot alpha 1, cot alpha 1. Okay. And what is U1? U1 is this one. So, U1 is this minus this. So, now this one is VW1, Vf1 cot alpha 1. Now, this one is Vf1 cot of this angle, see that cot of this angle, which is 180 degree minus beta, and cot 180 degree minus beta is minus cot beta. So, therefore, this will be U1 will be Vf1 cot alpha 1 minus minus will be plus Vf1 cot beta 1. This is what minus this in terms of beta 1 is Vf1 minus this length, Vf1 cot of this angle, cot 180 degree minus beta 1, that means minus cot beta 1, that is why plus. So, now it can be written since Vf1 is Vf2 is Vf. So, simply I write Vf square cot of alpha 1 into cot of alpha 1 plus, this is the convention, that means in terms of the blade angle and the inlet velocity angle, and this angle is the outlet angle of the guide vanes, because the purpose of the guide vanes or wicket gate is to convert the pressure energy into kinetic energy and to guide the water correctly into the what is that figure, correctly into the runner. That means this will give a correct entry to the runner, so that the relative velocity is equal to the angle of the runner blade. So, therefore, the absolute velocity direction at the inlet with the tangent is the angle of the guide vane at the outlet with respect to the tangent. So, this is a geometrical parameter cot alpha 1 plus cot beta 1. Now, if I want to write the expression of hydraulic efficiency, what I will do? Give me a page. Now, I write the expression of hydraulic efficiency. Now, hydraulic efficiency or the blade efficiency, whatever you call, is defined as the work developed, that means VW1 U1 by G, that means simply which I have got Vf square cot alpha 1 plus cot beta 1 divided by the energy at the inlet to the turbine. I do not know energy at the inlet to the turbine, that is the energy at the inlet to the blade, that I do not know. I only know the head delivered by the blade, but this inlet energy I can know other way, that if head delivered is added with the losses, that will be the head available at the inlet. So, head available at the inlet will be this plus loss. So, this one Vf square cot alpha 1, that means it is other way, this plus loss, that means the work head developed by the turbine is the inlet head minus loss. Now, I add. Now, if we discard the viscous losses in the runner blades, which is usually less as compared to the kinetic energy loss at the outlet of the runner, then we write the kinetic energy at the outlet of the runner is the V2 square by 2G, and V2 is Vf2 is Vf, that means I can write Vf square by 2G. Now here you can ask me, sir, it is not the actual loss to the turbine, because turbine actually has a draft tube, and through the draft tube when it is rejected at the tail race, the velocity is very less. So that is the wasted, but when you consider as the hydraulic efficiency of the runner or the blade, then you have to take care of Vf square by 2G as the loss, because this is the exit from the runner. So now if you do it, you get an expression, Vf square will be cancelled out, cot alpha 1 plus cot beta 1 divided by this thing is the Vf square, Vf is cancelled out. So 1 plus 2 cot alpha 1 into cot alpha 1 plus cot beta 1, and if you make an arrangement plus 1 minus 1, this ultimately you can show that this equals to eta H or eta B, the blade efficiency. Sometimes eta H means hydraulic efficiency of the blade. It can be expressed as, this is a conventional expression, 1 plus 2 cot alpha 1 plus cot beta 1. Well, okay. Okay, this will be this is VWU2, because here 2G is not there, but I write in terms of the head. So better I divided it by G, or otherwise you can take I divided it by G, or what is that, if is G not there, it will be Vf square by 2, because I am always explaining in terms of head. So this is the work head developed, work head plus the exit kinetic head. But if you tell in terms of mass, then this G, then the word head will not go. Head is the energy per unit weight, otherwise you discard G and Vf square by 2. Okay. Now we will develop an expression of specific speed. It is all now algebra that I am doing, not much, not at all of any fluid mechanics, consideration. Now specific speed of a turbine, as you know, is given by Np to the power half divided by H to the power, it is dimensional specific speed 5 by 4. Now it is customary that this head is power is expressed in terms, this is what is that, first of all this is rotational speed, this is the power developed by this turbine, and this is H head available at the turbine. You have to understand the nomenclature, that is very important. A specific speed is defined earlier also, last class I told, rotational speed, power developed by the turbine and head at the inlet to the turbine. Now if we write power in terms of the head, rho q g h into eta hydraulic, that means rho q g h is the, what is this power, h is the head delivered by the turbine into g, that is work energy per unit weight, g into mass flow rate rho q. This is the power or the power head available at the turbine, and this is multiplied with hydraulic efficiency give power. So if you substitute this, then you will get NST as, if you take N outside and rho q, this is the rearrangement g and eta h to the power half and h to the power minus 3 by 4. This h to the power 5 by 4 is in the denominator, h to the power minus 3 by 4. Now if you substitute n and h, now n is what is n? Pi d by u, and if I write this at the inlet, it will be pi d1 by u1 or pi d2 by u2. N is constant. Now this pi d1 u1 by pi d1, I am sorry, it is u1 by pi d1, I am sorry. Now this u1 by pi d1, I am extremely sorry. This u1 we have already seen that, what is u1? u1 is Vf cot alpha plus. So in such small space, it is very difficult to show everything, that is the problem, small space. So u is this one u1, it is Vf1 minus this one, that is Vf1 cot alpha 1 plus Vf1 cot beta 1, and Vf1 is Vf, so Vf cot alpha plus cot alpha 1 plus cot beta 1 divided by pi d1. All right. Now this H, what is this H? H is the head at inlet to the turbine, that is Vw1 U1 by G plus the losses, that means Vf square by 2G, we already developed. And what is Vw1 U1 by G? This will be Vf square cot alpha, we already, Vw1 is Vf cot alpha, that means we already developed, that is Vf square cot alpha 1 into cot, it was already developed cot beta 1 plus Vf square by 2G. So this is nothing but the head at the, this was already developed while deriving the expression of hydraulic efficiency. So if you now put this value of H and this value of N here and make some algebraic rearrangement and algebraic manipulations, is simple at school level algebra, and you get an expression which you do not have to remember, just for your information I tell that this is one thing which I also do not remember. I have to see and write 2 to the power 3 by 4 G to the power 5 by 4 rho eta H to the power half. Now here another thing I have forgotten to tell, that when we have made this Vf here, we have to express Vf, the flow velocity, in terms of the flow rate. If we express volume flow rate as Q, then flow velocity can be expressed in terms of the area. What is this area? Pi d1 into the width. That means this flow velocity here is getting an area, this is the circumference that I tell you, that flow velocity here in the radial direction, the cross sectional area is pi d1 at the inlet into B. B is the width of the blade perpendicular to this plane, and this width depend upon the specific speed. Higher is the specific speed, that means lower is the head, more is the width, to have a more cross sectional area to accommodate more flow. So therefore this is the width or height of the runner, as you tell, and the area is pi d. This is the perimeter circumference time this, and pi d1 b1 is pi d2 b2, pi d1 b1 is pi d2 b2. So this width is accordingly changed so that this is being satisfied. Why? Because Vf is same, because the flow velocity, because Q rather is flow velocity times the cross sectional area, which is either this or this. If this has to be same under steady state, as you know from fluid mechanics basic idea, so therefore this has to be adjusted. So at the inlet, therefore if we write this Q pi d1 b1, this has to be replaced, Vf has to be replaced by this, then finally it comes this B by pi d1, well, half cot alpha 1 plus, this is simply school level task, into 1 plus, you can do it as your exercise, you will get this thing cot, or you can see any book. In my book it is deduced nicely. That means this is an algebra, no further deduction is required, 3 by 4. This is the expression of specific speed. Now I give you some typical values. Now variations of geometrical parameters and all these things, already I have explained you the value of this what is called this, already I explained you the diagram of this expression for the hydraulic efficiency. Now I will do the expression for the degree of reaction, R. Now degree of reaction is again the static head developed divided by the dynamic head developed. Now dynamic head developed, total head developed, sorry, total head developed is Vw1 U1 by G. Already I know, that is already many times we have done Vf1 square cot alpha 1 into cot alpha 1 plus cot beta 1. This is the total head developed. Now, how much is the static head? That without any information on U1, U2, VR1, VR2, I cannot tell, because this is U1 square minus U2 square by 2g plus VR2 square minus VR1 square by 2g. I do not know this information about the relative velocity and the blaze speed at outlet and inlet. Sometimes another trick is written that this minus, because this is the total head developed, V1 square minus V2 square by 2g. So, this minus this, that means this is done in this way, that Vf was cot alpha into cot alpha 1 plus cot beta 1 minus the change in the dynamic head, kinetic energy, that is V1 square minus Vf square, that is the outlet kinetic energy, divided by, now here again I am not writing the g, beta 2. If you write g, then there will be 2g, so beta 2. So, this is per unit mass basis, that means this is the energy developed per unit mass. If you call it as head by g, then it is g, then this is the total head developed or total energy developed per unit mass, energy developed per unit mass minus that due to the change in the kinetic energy per unit mass. That means this is the static head developed. If you do this thing, ultimately you will clear this thing, Vf will be cancelled out and straightforward it will come cot alpha 1 divided by 2 cot alpha 1. These are all trigonometry, no fluid mechanics. Now, I will give you some value, I will tell you some typical values, design values for this. The Francis turbine, the value of beta 1, which is very important, usually varies from 45 degree to 120 degree. These are some information, this is not concept. The alpha 1 is varying from 10 to 40 degree, and the values of the diameter of the runner, the blade width and the diameter of the runner at the inlet varies from 1/20th. Again I am telling it is directly proportional to the specific speed. Specific speed, this is dependent on specific speed, usually in the range of 50 to 400. What is mean? In the range of means, beyond this range of the value of the specific speed, which is the combination of this Np to the power Np and H, the turbine works miserably. That means not at an efficient condition. That means in this range the turbine works more efficiently. So, therefore, when the combination of this in an actual power station falls within that range, we use a Francis turbine. Okay. Now, next what I will do is now what I will do is the draft tube. Now, I already told you about the draft tube, that this is a tube which is very important, which is given at the outlet of the runner to decrease the velocity, so that the loss of kinetic energy, they can focus the field, the loss at kinetic energy at the outlet from the runner of the turbine is reduced. So, to increase the effective head, and turbine can be set at a higher level from the tail race. This is the purpose of the draft tube. But at the same time I showed you that if you provide a draft tube, the pressure at the inlet of the draft tube or at the exit of the runner is below the atmospheric pressure by writing the Bernoulli's equation at the inlet to the draft tube and at the exit. This is from common sense, because if you have to make a flow which is discharged at atmospheric pressure, and in course of flow pressure is increased because of the decrease in velocity. So, pressure at the upstream has to be lower than the atmosphere, and if the velocity at the inlet is more, so it will be more low, it will be much lower than the atmosphere. This is from common sense also, one can tell by writing the Bernoulli's equation also. So, therefore, one has to be very careful about designing a draft tube. So, now draft tube is designed in this way, that there are certain straight type draft tube. This is a straight draft tube, divergent part. There are some simple elbow type draft tube. This is an elbow type draft tube, which is an elbow cross section. This minimizes the losses due to separation it makes a flow uniform. This is an elbow type with varying cross section. Most important thing is that in fluid flow, that whenever you design a divergent section, you should be very particular about the included angle of the divergent section. When this is curved, at any point the included angle between the tangent at these 2 points. Here it is straight, the included angle between these two should not be more than 8 degree, it should be less than equal to 8 degree to avoid the boundary layer separation. Probably this has been told earlier by Professor Sandeepan Ghosh Mollik, that when the flow takes place in a divergent duct, how the boundary layer separation takes place and the angle has to be restricted. Now most important part, again I am coming for the reaction turbine, is the draft tube, Now again I am telling the draft tube, to understand very carefully, let us do this thing, the draft tube, and this is the inlet of the draft tube, and here is the turbine. This is the turbine T, this is the draft tube. To understand the draft tube principle, you must do that draft tube, and this is the tail race. So this is the flow direction. So let us tell 2 is the inlet and 3 is the outlet of the draft tube. 2 is the inlet of the draft tube means 2 is the outlet of the runner, 1 is the inlet of the runner. Let the runner or the turbine, the draft tube is also a part of the turbine, that is why I am not telling turbine, I am telling the runner. Let the runner along with the scroll casing, guide vanes, all these things is at a height z from the tail race. Then writing the Bernoulli's equation, P2 by rho g in absolute pressure term plus V2, again I am writing, this has been done, V2 square by 2g plus z is equal to P3 is the atmospheric pressure discharge plus V3 square by 2g plus z plus h. Now for our easier understanding, let us neglect this, because usually if it is cross section is large, that V3 is negligible compared to V2, and you neglect the viscous losses here, the short tube usually the frictional losses is less. So it will not hamper our understanding. Our main understanding is that P2 by rho g is now, that is the pressure at the inlet to draft tube, which I told comes from the common sense, has to be lower than this value. That means you have to be very careful that this runner should not be placed at a great height, so that you have to incorporate a long draft tube. It is very tough, because this will create a much lower pressure at the inlet. This is the most vulnerable section where the pressure is the minimum. So pressure is always above atmospheric, so that pressure gradually increases. This is the diverging section where pressure increases and finally meets the atmospheric pressure. So common sense tells everywhere the pressure is below the atmospheric, but it does not matter if P2 is greater than PV, that vapor pressure. Otherwise liquid will boil off and cavitation will start taking place. So therefore one has to be very careful about the height at which the runner should be placed, and also the velocity, that means runner should develop work and the runner blades are so designed, that is the concept, so that it must discharge the liquid or the water here at a velocity not very high. Though this velocity is not coming as far as the head final or net head obtained from the turbine, because ultimately this is the velocity of discharge which is lost, because the draft tube itself forms the part of the turbine. So this is not the final discharge point of the turbine. So loss of kinetic energy is V3 square by 2g, which is substantially less, but an increase in this creates a pressure lower than that, and that creates a problem of cavitation when the water starts boiling. And what happens? The cavitation is phenomena when water starts boiling. Before that, air bubble release, which causes bubbles of vapor which rapidly moves, strikes the surface of the conduit and they collapse and erodes the surface. So this is a serious damage of the equipment, and this is known as cavitation. In short, this is the cavitation. Now to avoid the cavitation, therefore what has to be done I have told. Now you see the cavitation is that there is a term known as net positive suction head. There is a term known as net positive suction head, which is usually written like NPSH, net positive suction head, NPSH. It is by definition is this NPSH is equal to the inlet head or the outlet head. Now, if I define again this as the outlet, that means the runner this as the outlet, then or does not matter, that is the terminology, that means inlet to the runner or outlet from the turbine at this portion, if it is defined as the E, that P by rho g plus V square by 2g, if these two pressure head and the velocity head together, so that this 2 is written as the E in terms of E. Earlier we wrote the section as 2, that the outlet. Now I write section E, then it is, because in book you will see this rho g, that means by definition the pressure head and velocity head at the outlet from the runner of the turbine and inlet to the draft tube, inlet to the draft tube, that means the sum of the pressure and velocity head minus the head corresponding to the vapor pressure or vapor pressure head. This is known as net positive suction head. All right, this is written like that. Now I know that you have seen that P by rho g plus V square by 2g, that means this thing, this thing is nothing but P atmospheric by rho g minus Z. Okay. All right. Here what I have written? That Z is not be there. Sorry, I am sorry. So therefore, this is P atmospheric by rho g minus Z. So one can write this as P atmospheric by rho g minus Z minus PV by rho g. Well, now a parameter is defined as Thomas cavitation parameter. Thomas cavitation parameter, Thomas cavitation parameter, which equals to NPSH by H, that is by definition, that means this divided by H, that means this is defined as a Thomas cavitation parameter. This in terms of this, if I write, sorry, this here, if I write, this is the NPSH divided by the head H, head of the turbine, that means it is the head, that is the head available at the turbine. This is this one, the NPSH, this you can write in this fashion also, P atmospheric by rho g minus Z minus PV by rho g. Okay, now again I write Thomas cavitation parameter is defined as Thomas cavitation parameter sigma. Thomas cavitation parameter is defined as Thomas cavitation parameter is defined as Thomas cavitation parameter is defined as NPSH divided by the H, and this NPSH is the nothing but definition is the total head. Total head means only pressure and velocity head at inlet to the draft tube or at exit from the runner minus the head corresponding to vapor pressure. This can be written as this by applying the Bernoulli's theorem here and here, as I already did. Space is so small that I have to refer like that, already did. This was by mistake, Z was here. So P atmospheric by rho z, in consideration of viscous loss to be negligible and the velocity of discharge at the outlet of the draft tube is much smaller compared to that at the inlet. So with that we can write this. So therefore we can write P atmospheric by rho g minus Z, so that P atmospheric by rho g minus Z minus PV by rho g. This is known as Thomas cavitation. How does it work in practice? One critical cavitation parameter is defined in practice, critical cavitation parameter. Critical cavitation parameter, that sigma c, which is defined in the similar way, but here the critical cavitation parameter, instead of PV by G, it can P atmospheric by rho G minus Z minus the PE by rho G, that means the actual pressure at the outlet to the turbine. Now, in any case PE should have to be greater than PV for the smooth operation. To avoid the cavitation, PE has to be greater than PV. So, if PE is greater than PV, then what happen? That by H, that sigma has to be greater than sigma C, because PE is greater than PV, because this should not fall below PV to avoid cavitation. So, therefore, what is done is Thomas cavitation parameter is known, because P atmospheric is known, vapor pressure of the water is known at the working temperature, and we know the head available. So, if we can know from our design that what should be the exit pressure depending upon the design of the turbine runner, then we must check that sigma should be greater than sigma C, and accordingly we can set the turbine at that height. That means installing the turbine at a particular height depends upon by checking this sigma and sigma C, that sigma should be always greater than sigma C. Usually this value is known and does not change much in case of a turbine, it is runner design, but usually in installation we have to find out at which level from the tail race, at what height we will set the runner to avoid the cavitation. There we check the critical cavitation parameter by taking arbitrary values of Z, so that sigma should always be greater than sigma C with some margin, so that the cavitation does not occur. So, this is the concept of NPSI, net positive suction head, cavitation, and the function of the draft tube. Now, I will tell you one thing, that already I have told you this reaction turbine is well suited for lower head. They should convert this thing, I do not know why. The reaction turbine is well suited for a lower head. What does it mean? The reaction turbine usually work much better or higher efficiency when the head is low. When head is low, a substantial power to be developed, flow rate has to be more. So, therefore, reaction turbine should be designed in such a way it must accommodate more flow at the lower head, so that it acts efficiently and delivers substantial power. Now, to do so, the design of the turbine blade should be made like that. In case of a radial flow turbine, which is the flow is in the radial and tangential direction, that means it has got both tangential component and radial component. Bulk flow is in the radial direction, radially inward flow, as you know. In case of a reaction turbine, it comes like that, then immediately it turns to the right angle, that in axial direction. In a horizontal plane, it comes in a radial inward direction, then it immediately turns to the axial direction, horizontally downward through a draft tube to the tail race. Now, what happens in a reaction turbine, because of its limitation, that of the lower area at the outlet and the type of the shape of the blade, sometimes it cannot provide a higher flow rate when the head is substantially low. So, when relatively head is lower, it is difficult for a radial flow turbine for its inherent design to provide a higher flow rate and at the same time a lower exit velocity to be maintained to avoid the cavitation. So, this is not possible. So, therefore, this concept evolves the birth of axial flow turbine, where the flow is in the axial direction and the blades are made in such a way it gives a cross sectional area much higher as compared to a radial flow, so that we can accommodate more flow rate which can work efficiently at a relatively lower head. And this is the concept. For less time I cannot explain this thing. The Kaplan turbine, this where is this figure? No, that figure is here. So, therefore, I will show you a picture of that type of turbine is the Kaplan turbine. Just I will show you a simple picture of this turbine. This turbine is known as axial flow type of turbine. Axial flow type, not radial flow type turbine. Now, just now I have told you the concept of this axial flow type turbine. This turbine is like this. This was also invented by another scientist Kaplan, and it is known as Kaplan turbine. This is used in power plant in practice when the head is relatively lower. Here you see these are the guide vanes. These are the guide vanes through which the fluid approaches via penstock. Then this changes, the guide vane angle is such, changes the flow direction right angle to the axial direction, and these are the blades. If you take a sectional view here plan, so you will see this. This is a sort of a propeller. Sometimes this is known as propeller type of turbine, Kaplan turbine, and the flow is like this. So, this type of turbine accommodates more flow and act at a relatively lower head available more efficiently. That means the specific speed of this type of turbine, which is given as Np to the power half h to the power 5 by 4, this is much higher because head is low. Okay. This is the. Now, I will show you the characteristic curves of the turbine. Now, characteristic curves of the turbines are shown like that. Now, I have told that a characteristic curve which is governed by the function of pi terms, probably you remember q by nd cube, gh, mainly these 3 pi terms n square d square and p by rho n cube d phi, and a combination of these 3, this divided by this into this gives you the hydraulic efficiency. So, these 3 pi terms are the major pi terms. As a combination we can get the hydraulic efficiency. Now, these characteristic curves of a fluid machines are given in terms of the variation of these characteristic pi terms of a homologous series of the turbine, so that one curve represents the characteristic curves for other turbines of the same series. So, Francis turbine is such a homologous series. Now, for all Francis turbines, this is the characteristic curve where these are the characteristic parameters usually referred to, which are the combinations of these pi terms, which may not be directly these pi terms, but the combination. This is some normalized capacity or discharge, this is normalized power. So, these are the things. Curve 1 is the normalized, and these are all drawn with respect to a normalized speed n, and this is the typical thing. This is number 1 curve is of the normalized discharge, 2 is the hydraulic efficiency which reaches a maximum, and this is the corresponding discharge, and this 3 is the power delivered by the turbine. These are the typical characteristic curves which you can get in any book, and this is the curve describing all the turbines of the homologous series of Francis turbine. Now, I will show you another curve which is very interesting now. For the lack of time, I could not describe all sorts of hydraulic turbines. You can go through my NPTEL lectures on fluid machines, which will be uploaded within a couple of days. There all sorts of turbines are discussed with a much longer time period during, but now I tell you one very interesting thing. There is a class of turbine known as Pelton wheel. This is an impulse turbine, that is Pelton wheel. Now, impulse turbine, as I have given an example as a paddle wheel, similar type of thing is there for the Pelton wheel, where the stator is a nozzle which converts the entire pressure energy which is coming from the fluid leading via the penstock, leaded via the penstock from the reservoir in the form of pressure, is converted completely into velocity and discharged into atmospheric pressure, which ultimately strikes into a number of blades tangentially and gives the power. I cannot tell anything more because I am not covering Pelton wheel now in this lecture. So, this is a category of impulse turbine. Now, Francis turbine we have discussed, and axial flow turbines, that is Kaplan turbines, which is evolved from the concept of the radial flow reaction turbine. This is axial flow reaction turbines which can accommodate more flow rate and work relatively more efficient at a lower head. This is axial flow turbine. What is shown here, the efficiency of each turbine versus the dimensional specific speed, dimensionless specific speed, not the dimensional, that means n p to the power half rho to the power half g h to the power 5 by 4. If you remember, this is the now here this curve represents that, does not matter if you take out g and rho, is the dimensional specific speed. Now this, if you see the maximum efficiency of the Pelton turbine takes place at a lower value of specific speed, which means the Pelton turbine works better when the specific speed is low, that means high head. So therefore when the head is high, available head, we prefer the Pelton turbine, whereas the head is relatively low because the Francis turbine works on the maximum efficiency or high efficiency range when its specific speed is relatively higher than that, that means a relatively lower head. Axial flow turbine works at a higher efficient level when the specific speed is very high, that means at a lower head. So this is in sequence, the impulse and reaction turbines, radial and axial flow are used when the head available varies. Okay. I think after this, this chapter is closed, and about hydraulic turbines I do not want to add anything because we cannot start anything because we have not gone through impulse turbine. So better we close this lecture, and I again suggest you read books, see my uploaded my NPTEL lectures which will be uploaded within a couple of days, so that you can understand very well the principles of other turbines when you go through the discussion of these principles of Francis turbine, a radial flow reaction turbines. Okay. Now before closing this session, I can take one or two questions maximum. Please.
1108.
তুমি answer দিয়ে দাও। 1108.
You are not audible.
পাম্পের গুণ আছে তো সব।
Good morning, sir.
Yes, good morning, please. Good morning.
Yes, sir. Yes, sir. I want to know that when a fluid passes through a diverging duct,
Yes.
so how velocity converts into pressure energy? What fundamental change takes place in fluid? So if you can explain it.
Okay, it has been told earlier, this is a fundamental principle. Okay, when a fluid flows through a divergent duct, by the application of the continuity equation, the velocity decreases. You understand? The area is increasing. So if you write the continuity equation under steady state, flow rate at each section has to be same, and the flow rate is expressed by the area times the average velocity at that cross section, or you can take an uniform velocity at that cross section. So therefore product of area into velocity, if it is an incompressible flow, rho is constant, has to be same at all cross sections, and this is the basic principle comes from the continuity, that when the section cross section increases, that means in a divergent duct, the velocity decreases. Now when the velocity decreases, what happens? Now consider an inviscid fluid. If you write the Bernoulli's equation, when the velocity is decreased, the pressure has to increase from the conservation of energy principle also. If you consider the mechanical energy conservation, which is the Bernoulli's equation, so velocity has to increase. However, the increase in velocity is not in correspond to the increase in velocity or the square of the velocity that is given by the Bernoulli's equation because of the losses. Okay. So from Bernoulli's equation you get the increase in pressure is the due to the decrease in the square of the velocities. That means it says physically that there is a decrease in the kinetic energy to manifest in terms of an increase in the pressure energy or increase in the static pressure. This is the principle. It comes fundamentally from the continuity equation and then the energy principle given by Bernoulli's equation. Okay. Okay.
Sir, it could be the mathematical explanation, but physically can we say that because of crowding of the fluid particle it happens?
That of course physically you can explain anyway, this is because of the
Yes.
crowding. Fluid is not crowding because the velocity is in a divergent duct, velocity is decreased. I do not know, I have never come across that crowding of the particles and all these things. If the velocity is increased from the energy principle, if kinetic energy is decreased, pressure energy has to be increased for the conservation of energy. Is as simple as that. So, you can think it in any way that as you like. Okay. Crowding of particles is a very confusing statement. I have never come across this type of statement. Crowding of particles.
Good morning, sir.
Good morning.
I am Sudhanshu from National Institute.
Yes, yes,
My
please,
question
please.
Can we apply principles of physical similarity
Yes.
flood control of river?
Oh, sure.
If yes, what type of similarity we can apply? Geometric similarity, kinematic similarity, or dynamic similarity?
Now, you see, I have taught you the basic principle of physical similarity, and I have told you, and again I am telling you, now to find out the similarity parameters or what are the parameters to be kept fixed to maintain the kinematic similarity, geometric similarity and the dynamic similarity, the very basic requirement I tell to know the problem physics, to know the physics of the problem, which will come from your brain, which will not be dictated by any equations. So, first of all you have to understand the physics of the problem first, in a way that what are the forces or applied on that problem or that physics of the problem, that the problem is governed by which forces, what is the flow geometry of the problem. Then only you can find out the relevant parameters for similarity of that class of problem. For example, flood controls, you have to find out what are the forces acting on it. A flood control situation probably is acted on by the gravity forces, is also acting on by the inertia forces, it is also controlled by the viscous forces. You have to understand the physics of the problem. Then you have to identify the parameters, physical parameters defining the problem. Then only you can find the similarity parameter. In this case, I feel the Froude number is the most representative parameter for the similarity, which defines the ratio of viscous force to inertia force, because in a flood control it is the local gravity which is very important, which creates this surface wave. I cannot tell you in much more detail, because then you have to understand the physics of this flood control things which are being dealt by the persons of ocean engineering. Okay.
Good morning, sir.
Yes, good morning.
Hello.
Good morning, yes.
Sir, my problem is from your dimensional analysis. Suppose the problem situation is like that, where we have to identify the different variables for governing a particular flow situation. How can we best identify all those variables governing the flow situation to make support the assessment of this all those non-dimensional numbers?
Yes, it is a good question, I appreciate, but I tell you to find out the dimensionless number governing a particular problem by the application of either Buckingham's pi theorem or Rayleigh's indicial method, you have to identify the physical parameters, and that have to be identified from the knowledge of the physics of the problem, that there is no formula of identifying this thing. For example, a fully developed pipe flow is being governed by viscosity, density, the reference velocity, average velocity or uniform velocity, the diameter of the pipe. Okay. So, all these things have to be known clearly. Usually what happens, I tell you, when we write the theoretical equations, for example, the Navier-Stokes equations for a particular problem, then we can find out by normalizing these equations what are the dimensionless terms governing that problem. From there also we get the dimensionless term directly, but from Buckingham's pi theorem you have to know the dimensionless terms where it is difficult, the problem is difficult to be solved theoretically, then the parameters defining the problem have to be known. There is no formula for it, that has to be known from the physics of the problem for our understanding of the problem, physical understanding of the problem. There is no other way out or no formula which will give you directly without understanding, okay, this is the problem, you push a computer button and tell is a problem of fully developed flow, problem of surface wave in a river, problem of capillary flow, they will give you the parameter. I do not know, if somebody uploads it from his knowledge, then it will be given, otherwise if you have to do it, you have to find out from your knowledge of the understanding of the physics of the problem. Any other question?
Thank you, sir. The second problem of mine is
Yes.
from the similarity analysis.
Please.
Similarity analysis.
Please.
Suppose we have to make a model for a particular prototype
Yes.
device. How shall I be able to know the non-dimensional parameters which should be compared for, which should be taken care of for deciding the model to be applied in the model formation?
No, model
creation.
No, you see, model you have to make first of all geometrical model. Geometrical model, first of all you see, first of all you have to find out the non-dimensional parameters. Just a simple example I am giving, that let us find out the model of a ship, for example. If we want to find out the model of a ship, you find out the resistance of a ship depends on the Froude number, Reynolds number and its non-dimensional geometrical parameters, because the resistance of a ship, if you want to find out the power of a ship, you have to find out the resistive force. Now, the resistance of a ship is guided by the height of the surface wave, which is controlled by the local gravity. Then it depends upon the viscous force of the water passing through the ship in the form of skin friction drag, form drag. So, therefore, it is the viscosity that controls the physics. So, if you know these things from your understanding of the physics, you write the parameters which are controlling the problem, like local gravity g, like viscosity, density, the velocity of the ship, characteristic velocity of the ship, characteristic length, you arrive at the parameter, non-dimensional parameter Froude number, then you find out the Reynolds number, and then if you take different dimensions, now come here, that we always take a characteristic dimension in our dimensional analysis, but there may be 3-4 dimensions, we know the particular object, ship, you can take 2-3 linear dimensions, for example L1, L2, L3, for example in a cylinder L and D. So, similarly if you have 2-3 linear dimensions, one rule of dimension analysis, it is obvious, you can understand that if there are 3 parameters of same dimension, their ratio will automatically become a pi term, and if you follow the dimension analysis of Buckingham, you will get that ratio. If there are 3 lanes L1, L2, L3, you will see L1 by L2 is one pi term, L1 by L3 is another pi term. So, now this question is that what value of L1 by L2 and L1 by L3 I will make it in my laboratory, I will reduce the size of the ship if the size of L1 is something in the ship, so that I have to maintain L2 is some, then L1 by L2 is same in my experimental or laboratory model. In that case, what scale factor I will use, that depends upon my availability of space in the laboratory, and at the same time when I reduce that dimension by the scale factor, now with that reduced dimension, when I will calculate my Froude number and Reynolds number with the viscosity and density available, then what I will do, that I have to see that this matches with the actual Reynolds number and Froude number in practice. Try to understand, because I will do the experiment on the laboratory, the model experiment, so that all the dimensionless parameters should correspond to the same range as that in practice. That means when I will model, make the geometrical model by reducing the dimension, that means L1 by L2 and L1 by L3 keeping same, but L1 is reduced by a factor, for example 1/10, L2 is by 1/10, L3 by 1/10, then we have to be careful that with this reduced dimension, when I will define the Reynolds number and Froude number of my laboratory model, that should corresponds to the Reynolds number and Froude number of the actual case. So, that means the parameters involving a pi term has to be adjusted in such a way, so you can have an arbitrary choice, but the restriction is that combined parameters defining a pi term should correspond to the range in the practice. Okay. Thank you. I think that is the last.
Sir, again,
One more. আচ্ছা আমি যখন বলবো তখন ওরা একটু আমাকে হ্যাঁ আই উইল ওরা দেখতে পাচ্ছে ওরা দে আর সিইং ইট ওকে
Hello, sir.
ইয়েস প্লিজ
Hello, sir.
প্লিজ
Good
প্লিজ
morning, sir.
প্লিজ
Sir, my question is, while calculating the hydraulic efficiency of Pelton turbine,
Pelton I
should
have
we
not read.
consider nozzle as a
Yes, please.
nozzle as a part of turbine? Means while to calculate the hydraulic efficiency of Pelton turbine, in the denominator, should we take potential energy or kinetic energy?
Okay, it's a good question. Now, while we calculate the blade efficiency of a Pelton turbine, not the hydraulic efficiency, blade efficiency or hydraulic efficiency of the wheel, then definitely the kinetic energy at the inlet is the input energy. Then what we will do, we will find out the work head developed by the wheel of the Pelton turbine, which is Vw2 U2 minus Vw1 U1 minus Vw2 U2 by G, and inlet will be the inlet energy, the kinetic energy is the energy inlet to the blade. So, this is the blade efficiency, usually this is termed as blade efficiency or hydraulic efficiency of the blade. But if you have to find out the hydraulic efficiency as a whole of the turbine consisting of both the nozzle, which is the stator of the turbine, plus the wheel, then definitely you are correct, your input energy is the pressure at the inlet to the nozzle. Difference is that the losses in the nozzle, frictional losses in the nozzle. So, therefore, pressure at the inlet to the nozzle is the input energy when you define the hydraulic efficiency of the entire turbine. But if you find out the hydraulic efficiency of the wheel, it is known as blade efficiency of the Pelton wheel, then kinetic energy at the inlet to the blade is the inlet energy. Okay. I will stop here. Okay.
Sir, my second question is, hello, sir.
Please, this is the last question. Yes.
My
Please.
second question is, what is the physical significance of degree of reaction?
Degree
Does
of
the higher value of degree of react desirable?
no, it depends upon the operative conditions. I tell you the physical significance of reaction, degree of reaction, as I explained through these examples of paddle wheel and the launch sprinkler, that degree of reaction means a reaction turbine that the static head is being utilized to develop the power in case of turbine. So, how much static head will be utilized out of the total head in the turbine, how much will be the different distribution of kinetic head and the pressure head at the inlet to the turbine, it all depends upon the range of flow and the range of head available. So, one cannot say that how much reaction will be required, that is manifested through specific speed. For an example, when the head is low, then to get some substantial power, you have to devise a turbine which must accommodate high flow rate. So, a turbine which delivers power at a lower rate and higher flow rate, it has to work efficiently, it has to work on the principle of reaction. That means, if it works in the principle of impulse that it does in a Pelton wheel, what does a Pelton wheel? It acts in the situation where the head is very high, that means the reservoir at a great height, at high altitude. So, there it is possible to convert all the potential energy into kinetic energy thoroughly and by the impulse action to develop power efficiently. But it is not possible when the altitude is low, that means the energy available in the form of potential energy is low. There the reaction is required to develop power at a high efficiency. So, these are the things. Okay, this is very difficult to tell immediately that what should be the reaction and why it is. This is physically like this, it depends upon the operating conditions. Okay, thank you. Any other questions I tell you regarding fluid machines or any other part of fluid mechanics, you please ask, upload this, we will give you the answer. We will upload the answers from our side online. Okay,
Thank you, sir.
okay.
Thank you, sir. Over to you.
Okay.